Welcome to my microwave class. Hi there, welcome back to microwaves lessons. In today's video, we will discuss the concept of impedance matching networks using lumped elements. We will start by explaining why do we prefer using lumped elements over stubs. Then we quickly recall the conjugate matching theorem. Afterwards, we focus on lossless two-ports networks' role in impedance matching. Next, we introduce an extended version of the Smith chart that allows direct manipulation of admittances. Later, we recall the concepts of resonance, bandwidth, and Q factor, and relate them to the impedance matching concept. Finally, we present the main network topologies used in the field, namely the L, pi, T, and double L matching networks. For each circuit, we suggest an analytical and graphical design method. We start by presenting a VS between distributed and lumped elements. The table below shows why we should consider lumped elements over distributed elements whenever the two options are available. Overall, lumped elements are often the go-to choice for compact, flexible, and cost-effective matching networks. However, there are cases where distributed elements make sense, especially at microwave frequencies, where transmission line effects become more significant and parasitic components in lumped circuits are getting overwhelming. Let's now quickly revisit the conjugate matching theorem. Consider the figure below showing a simple circuit made up of a generator of internal impedance Zg and a load ZL. Of course, by the means of Thevenin theorem, the generator and its internal impedance could model the output port of a network, while the load could represent the input impedance of another network. In order to achieve a maximum power transfer from the generator to the load, the conjugate matching theorem states that ZL must be the conjugate of Zg. In real situations, this condition hardly ever occurs off the shelf, meaning it's unlikely that the output impedance of one stage perfectly matches the input impedance of the next stage. Here comes the magic of impedance matching networks. An impedance matching network is inserted in between the stages so as the generator perceives a load whose impedance is conjugate matched to it, while the actual load perceives a generator with an impedance conjugate matched to it, and everyone is happy. If the input impedance of the matching stage is Zin, and if its output impedance is Zout, then under conjugate matching, we must have simultaneously Zg equals the conjugate of Zin and Zl equals the conjugate of Zout. To avoid wasting power, it is desirable to use lossless impedance matching networks. The drawback of such networks is their narrow bandwidth and selectivity. At the opposite, lossy impedance matching networks are wideband at the expense of power losses. In this video, we will consider solely lossless impedance matching networks. Actually, when bandwidth is not a major concern, lossless matching networks are not chosen only for their advantage in reducing losses, but they are also appreciated because the simultaneous conjugate impedance matching condition reduces to only one condition. Indeed, it's easy to prove the following equivalence. If Zg equals the conjugate of Zin, then Zl equals the conjugate of Zout, and vice versa. The proof relies on the use of the impedance matrix representation, which in this particular case is composed entirely of reactive elements. The proof for the forward implication is provided below, and the same steps apply for the reverse implication. As a result, in order to achieve impedance matching, it suffices to enforce only one of the following conditions. Either Zg equals the conjugate of Zin, or Zl equals the conjugate of Zout. Let's now expand the Smith chart tool. The genuine Smith chart is already handy when working with impedances and reflection coefficients. The chart represents the locus of the reflection coefficient, which is then mapped to a normalized impedance thanks to a grid made up of R circles and X circles. R values are always positive, while x values can be positive or negative. The Smith chart relies on the use of a normalization impedance Z0, which is smartly chosen to ease solving problems. It could be the characteristic impedance of a transmission line, the load resistance, the internal resistance of the generator, or any other resistance which allows getting accurate results. In this video, we will use lowercase letters to designate normalized quantities. For example, if uppercase z equals r plus jx, then lowercase z equals z over z0, which is equal to lowercase r plus jx, where lowercase r equals r over z0 and lowercase x equals x over z0. Assume we want to compute the input admittance of the network depicted in the following figure. Analytically, we find y-in equals 4 minus 6.86 J millisiemens. Finding this result graphically involves the following steps. First, we locate the terminal load on the chart. So, from the uppercase ZL, we find the normalized ZL. The normalized ZL equals uppercase ZL over Z0, so ZL equals 1 plus 2J. Afterwards, we consider the corresponding admittance using the point diametrically opposite relative to the origin. We find YL equals 0.2 minus 0.4 J. The same steps apply to the reactance ZP. Starting from ZP equals J75 ohm, we normalize the reactance. We get the lowercase xp equals uppercase xp over Z0, which is equal to 1.5. Thus, reduced susceptance BP is equal to minus 0.66. Now, because of the parallel admittance association, we compute the sum and get y'(L) equals yl plus jbp, which is equal to 0.2 minus 1.06 J. Then, we are facing a serial association. Thus, we must convert y'(L) to an impedance by considering again the diametrically opposite point related to y'(L). We find z'(L) equals 0.17 plus 0.91 J. Then, we add the value of the series reactance to get the input impedance. Zs equals jxs, thus lowercase xs equals 2. Then Zin equals z'(L) plus jxs, which is equal to 0.17 plus 2.91 J. Again, we get the corresponding admittance by locating the point which is diametrically opposite to the origin. We read y'(in) equals 0.02 minus 0.34 J. Denormalizing y'(in) yields the uppercase y'(in). The uppercase y'(in) equals 0.40 minus 6.80 J millisiemens. As shown by this simple example, switching between impedance and admittance representations is quite challenging. To ease this operation, we suggest expanding the Smith chart to handle seamlessly admittances by superposing a new admittance mapping grid. The latter is obtained by mirroring the impedance mapping grid relative to the origin of the chart, so that the R and X circles are transformed into G and B circles. Notice that the positive susceptances are located under the x-axis, whereas the negative susceptances are above the x-axis. Let's use the new Smith chart to find the input impedance of our previous example. We start by locating ZL and ZP on the black grid. Then we read YL and YP equals JBP on the red grid. We find again YL equals 0.2 minus 0.4 J and BP equals minus 0.66. The association of the two admittances is obtained by summing up their values. Here again, y'(L) equals 0.2 minus 1.06 J. Notice that y'(L) is obtained by moving YL by an amount of BP equals minus 0.66 in the counterclockwise direction on the GP equals 0.2 circle. Thus, we will remember that a shunt inductor will move the admittance in the counterclockwise direction, while a parallel capacitor will move the admittance in the clockwise direction. From the location of y'(L), we read straight the value of z'(L) on the black grid. We find z'(L) equals 0.17 plus 0.91j. Then we locate the sum to get Zin. Zin equals z'(L) plus jxs, which is equal to 0.17 plus j2.91j. Notice that Zin is obtained by moving z'(L) by an amount of xs equals 2 in the clockwise direction on the r equals 0.17 circle. Thus, we will remember that in the series inductor, we will move the impedance in the clockwise direction, while a capacitor will move the impedance in the counterclockwise direction. Finally, we read the value of Yin corresponding to Zin on the red admittance grid. We get again Yin equals 0.02 minus 0.34j. The expanded version of the Smith chart turns out to be very handy when computing a mix of in-series and shunt reactive associations. It is precisely the feature that we will need when designing impedance matching networks. We will now explain the concept of Q factor and relate it to the bandwidth of a matching network. We already know that ideal reactive elements do not consume energy because they do not have any losses. However, real reactive elements do have losses. For example, an inductor has an inherent serial resistance, whereas a capacitor has parallel and serial loss resistances. The quality factor, or Q factor, is a measure of those losses relative to the stored energy. If we consider a cycle of sinusoidal excitation of angular frequency omega, we write Q equals 2 pi times the stored energy during one period over the dissipated energy during the same period. Or equivalently, the Q factor equals omega dot stored energy during one period over the average dissipated power. Based on this definition, it's easy to determine the Q factor for a serial or shunt configuration. When considering an inductor or capacitor of reactance Xs in series with a resistor Rs, the Q factor is Q equals the absolute value of Xs over Rs. For a shunt configuration Rp parallel to Xp, we can easily show that the Q factor is Q equals Rp over the absolute value of Xp. The proof is provided in the following sidebar. Let's find now the Q factor of a series RLC circuit. The Fresnel diagram shows that voltages across the capacitor and the inductor are out of phase. In terms of power, that means the capacitor and the inductor do not store energy simultaneously. 1/4 of the period, the inductance will store a magnetic energy EL, which is equal to half L times the squared magnitude of the current. Another 1/4 of the period, the capacitor will store an electrical energy EC, which is equal to half the squared magnitude of the current over C omega squared. The ratio between the stored energies is EL over EC equals LC omega squared. The ratio suggests that the energy stored by the capacitors differs from the energy stored by the inductor. The Q factor's definition is ambiguous in this scenario because of the lack of clarity on whether we should use EL or EC for its evaluation. However, at a special angular frequency omega 0 where LC omega 0 squared equals to 1, the stored energies are equal and the ambiguity is cleared. In this condition, we define unambiguously the Q factor as Q equals L omega 0 over R, which is equal to 1 over RC omega 0, which is also equal to 1 over R times the square root of L over C, where omega 0 is the resonance angular frequency of the RLC circuit. From elementary circuit theory, recall the relation between the bandwidth and the Q factor. Q equals omega 0 over delta omega. The proof is given hereafter. But what's the relationship between RLC circuits and matching networks? In the following figure, we know that impedance matching is fulfilled when ZL equals the conjugate of ZG, or equivalently, RL equals RG and XL equals minus XG. So, if XL is a capacitor, then XG must be an inductor and vice versa. Thus, the whole circuit is a series RLC circuit with R equals RG plus RL equals 2RG or 2RL. The resonance frequency of this circuit is defined by the condition XL equals minus XG. Thus, the impedance matching occurs only at a single frequency, leading to a narrow band matching network whose bandwidth is here again related to the Q factor with Q equals the absolute value of XL over R, or XL over 2RL, or the absolute value of XG over 2RG, and Q equals F0 over delta F. As a result, the higher the Q factor we will use, the narrower the bandwidth of the matching network we will get. In conclusion, when presenting the impedance matching network's topologies, we will always associate an expression of the Q factor as it will provide information about the matching network bandwidth. The steps involved in the Q factor's determination comprise transforming the network to an equivalent in-series circuit, summing up all inductive reactances, dividing this quantity by the sum of the serial resistances. Note that transforming any network to an equivalent series circuit is only valid at a specific frequency. Comparing any network to an RLC series circuit is thus only valid at resonance frequency. Therefore, the Q factor is only meant to give a rough evaluation of matching bandwidth. With all the necessary tools at hand, we will now proceed to discuss various topologies employed in the field, beginning with the L matching networks presented in the following figure. Here we suggest two configurations to match a terminal load ZL equals RL plus JXL to the generator of internal impedance ZG equals RG plus JXG. By convention, we will call these configurations the forward L matching network and the reverse L matching network. Currently, we are unsure which configuration will be functional. The goal of this section is to find the reactances X1 and X2 that will yield impedance matching. Let's begin with the forward L matching network configuration. The results for the reverse configuration are deductible from the forward configuration by swapping ZG and ZL. The conjugate matching condition theorem is our starting point. We have Zin equals the conjugate of Zg, where Zin equals Jx1 in parallel to Zl in series with Jx2. So Zin equals x1 times the ratio minus xl plus x2 plus jrl over rl plus j times xl plus x1 plus x2. The expression of Zin given hereafter is obtained when separating the real and imaginary part. Applying the conjugate matching condition yields a set of two equations with two unknowns x1 and x2. After several algebraic manipulations, we find two solutions for x1 and x2. Here they are. For the reverse configuration, it suffices to swap Zg and Zl to find the corresponding solutions. In order for topology to be realizable, it's necessary for the values under the square root to be positive. The following table summarizes all cases. For specific values of Zl and Zg, there are at least two solutions, while in certain cases we may have up to 4 impedance matching solutions. Choosing a particular solution depends whether we need a low-pass, high-pass filter, selective or wideband network. Let's estimate the Q factor for the forward L matching network. For this purpose, we first search for the series network, which is equivalent to the parallel left part of the circuit. We write Z left equals Zg in parallel with Jx1. Developing, we get the following expression of Z left. But as the left subcircuits and the right subcircuits are meant to be matched, then R left is equal to R right, which is equal to RL. Then we will find that x1 squared over d squared is equal to RL over RG. Thus, after some transformations, we find x left equals x1 times 1 minus RL over RG minus RL over RG xg. Finally, the net reactance of the circuit is sigma x equals to x1 times 1 minus RL over RG minus RL over RG xg plus XL plus x2. For the reverse configuration, it suffices to swap between Zg and ZL. The last equations represent the contribution of each reactive element present in the circuit. Of course, under matching condition, we will get sigma x equals to 0. Finding the Q factor requires the determination of the sum of all positive constituents in sigma x. Thus, Q equals to the sum of all positive terms in sigma x over 2RL. Or equivalently, Q equals minus sum of all negative terms in sigma x over 2RL. Since we lack information about the signs of xg and xl, and as the relationship between rg and rl is unknown, it is impossible to derive a simplified formula for the Q factor that covers all scenarios. However, things get much simpler when xg equals to xl, which is equal to 0. In this case, the sum reduces to sigma x equals x1 times 1 minus rl over rg plus x2. Because we have only two terms, then one must be positive and the other negative. Therefore, Q0 equals the absolute value of x2 over 2RL, where x2 equals epsilon alpha 0 RL and alpha 0 equals the square root of Rg over RL minus 1. Consequently, in this simple case, we get for the forward configuration, Q0 equals the square root of Rg over RL minus 1. Hence, as the value of Rg increases relative to RL, the circuit selectivity will also increase. It's time for an example. Consider at f equals 1 GHz, designing a network to match a load impedance ZL equals 50 minus J150 ohm to a source impedance Zg equals 250 minus J100 ohm. Note that the negative reactance of the load and the source correspond to capacitor CL equals 1.1 picofarad and CG equals 1.6 picofarad respectively. The application of our developed formulas yields 4 circuits, 2 forward L-matching network solutions S1 and S2, and 2 reverse L-matching network solutions S3 and S4. The estimated Q factor and bandwidth are also computed. Based on this example, it appears that the Q factor only brings a general indication of the bandwidth, but it still gives us a qualitative indication, helping us predict which circuit will have a greater bandwidth. The following figures illustrate the behavior of the transfer function S21 of f of the matching network, while comparing it to the response of an RLC circuit characterized by the same Q factor. Among the 4 solutions, we get a high-pass filter and 3 selective filters. Solution 2 is very selective compared to solution 1, while solution 3 exhibits a moderate bandwidth. The 4th circuit is the great choice to consider if a wide bandwidth is required. Besides bandwidth aspects, components value can also influence our choice, as certain values may not be workable. Let's find now these solutions using the Smith chart. The idea is to start from the load and add consecutively in series and shunt reactances until we reach the conjugate of the generator impedance. Finding the matching network comprises finding paths from the starting point to the target. First, we must choose a normalizing impedance. In our example, it could be Rg equals 250 ohm or RL equals 50 ohm. As our target is Zin equals the conjugate of Zg, we suggest using Z0 equals Rg equals 250 ohm. The next step involves locating Zl and Zin on the chart using their reduced values, Zin equals 1 plus 0.4j and Zl equals 0.2 minus 0.6j. From the chart, we extract the corresponding admittances Yin and Yl. Upon completion, we mark R circles and G circles that go through Zin and Zl. When considering series reactances, the point on the R circle will move clockwise for inductors and counterclockwise for capacitors. When dealing with shunt susceptances, we will move on the G circle. Inductors move the point counterclockwise, while capacitors move the point clockwise. Because the L matching network comprises one shunt connection and one in-series connection, we must necessarily use one R circle and one G circle. The intersections of those circles can be considered as bridges used to reach the target point. Depending if we are solving for the forward or reverse configuration, we could either start with an R circle or G circle. Now we identify the paths from ZL to Zin. As we have 4 intersection points M1 to M4, then 4 solutions are conceivable. The first path consists of moving from ZL to the point M1, then from M1 to Zin, where M1 corresponds to Z1 equals 0.2 minus 0.44J, or Y1 equals 0.85 plus 1.9J. When traveling from ZL to Z1, we take the clockwise direction on the R equals 0.2 circle. Thus, we are adding an inductor whose reactance is the difference between the reactance of the starting point and that of the ending point. We write x21 equals x1 minus xl, which is equal to minus 0.44 minus 0.6, which is equal to 0.16, which corresponds to uppercase x21 equals 40 ohm. From Z1, we move towards Zin on the j equals 0.85 circle in the counterclockwise direction. Thus, we are adding an inductor whose susceptance is B11 equals Bin minus B1 equals minus 0.35 minus 1.9, which is equal to minus 2.25. It corresponds to a reactance X11 equals minus 1 over B11, which is equal to 0.44. Thus, uppercase X11 equals 110 ohm. Note that as we began our move on the R circle, that corresponds to a forward L matching network. The second forward L matching solution comprises using point M2, which corresponds to Z2 equals 0.2 plus 0.44J, and Y2 equals 0.85 minus 1.9J. When walking from ZL to Z2, we take the clockwise direction on the R equals 0.2 circle. Thus, we are adding an inductor whose reactance is X22 equals X2 minus XL, which is equal to 1.04. It corresponds to uppercase X22 equals 260 ohm. From Z2, we move towards Zin on the G equals 0.85 circle in the clockwise direction. Thus, we are adding a capacitor whose susceptance is B12 equals 1.55. It corresponds to a reactance X12 equals minus 1 over B12, which is equal to minus 0.645. The corresponding uppercase reactance is X12 equals minus 161.3 ohm. In the next steps, we will determine the reverse L matching solutions. We use the point M3 corresponding to Z3 equals 1 minus J and Y3 equals 0.5 plus 0.5 J. When traveling from ZL to Z3, we take the counterclockwise direction on the G equals 0.5 circle. Thus, we are adding an inductor whose susceptance is B11 equals B3 minus BL, which is equal to minus 1.0. It corresponds to a reactance X11 equal minus 1 over B11, which is equal to 1. Uppercase X11 equals 250 ohm. From Z3, we move towards Zin on the R equals 1 circle in the clockwise direction. Thus, we are adding an inductor whose reactance is X21 equals Xin minus X3, which is equal to 1.4. So uppercase X21 equals 350 ohm. As we start moving on the G circle, remember we are constructing a reverse L matching network. The second reverse L matching solution comprises using point M4, which corresponds to Z4 equals 1 plus J, or Y4 equals 0.5 minus 0.5 J. When traveling from ZL to Z4, we take the counterclockwise direction on the G equals 0.5 circle. Thus, we are adding an inductor whose susceptance is B12 equals B4 minus BL, which is equal to minus 2.0. It corresponds to a reactance X12 equals minus 1 over B12 equals 0.5. Thus, the uppercase X12 equals 125 ohm. From Z4, we move towards Zin on the R equals 1 circle in the counterclockwise direction. Thus, we are adding a capacitor whose reactance is X22 equals Xin minus X4, which is equal to minus 0.6. The uppercase corresponding reactance is X22 equals minus 150 ohm. When we use the L matching network, we observe we lack the ability to control the circuit's bandwidth. What if we want a more selective circuit? Here, the pi matching network comes in help. The following figure shows the new matching circuit made up of reactances X1, X2, and X3. Thanks to this topology, we aim to convert ZL to the conjugate of ZG. For this purpose, we split the matching circuit into two sub-circuits as shown in the following figure. To realize impedance matching, it suffices that the output impedance of the left circuit be equal to the conjugate of the input impedance of the right circuit. That is, Z left out equals the conjugate of Z right in. Because we have three unknowns and only two real equations, we can add an equation which will enforce the value of the intermediate impedance. We write Z left out equals the conjugate of Z right in, which is equal to R pi. Hence, we divided the pi matching network into two L matching networks. To guarantee the actual existence of these L matching circuits, we choose R pi so that R pi is smaller than RL and R pi is smaller than RG, or equivalently, R pi is smaller than the minimum of RL and RG. To find the expression of the reactances, it suffices to apply twice the formulas developed for the L matching network. So we get the expression of x1 and x'2, then we get the expression of x3 and x2, and obviously x2 equals x'2 plus s2. When xl and xg equals to 0, then we get much simpler expressions. As we have two solutions for each subcircuit, we end up with four combinations, each having a specific Q factor. The previous part of the video shows that increasing the ratio of the generator resistance to the load resistance leads to an increase of the Q factor. Therefore, choosing an intermediate resistor R pi much smaller than RL and RG will definitely raise the Q factor of the complete circuit. Actually, we evaluate later by summing the Q factor of the left and right circuit. Q pi equals Q left plus Q right. When the source and load impedances are real, the expression of the Q factor is simple. Here it is. Otherwise, we must give much care to the evaluation of Q left and Q right. For instance, to find Q left, we must consider again positive terms in sigma x left and divide the result by 2R pi. Then, to find Q right, we must consider again positive terms in sigma x right and divide also the result by 2R pi. Consider at f equals 1 GHz, designing a pi matching network in order to match a load impedance ZL equals 50 minus J150 ohm to a source impedance ZG equals 250 minus J100 ohm. The following table summarizes the solutions obtained when applying the developed formulas when using R pi equals 25 ohm. Here again, the Q factor only provides a rough estimation of circuit bandwidth. It's important to mention that the pi matching network achieves an average bandwidth 2.87 times narrower than the L matching network. Thus, we have successfully reached our desired goal. Choosing a smaller R pi will provide a much narrower bandwidth. Last word about the pi matching networks concern combining in series reactances x'2 and x2. When they are of the same type, that is inductive-inductive or capacitive-capacitive, then replacing the two components with only one equivalent component won't change the circuit behavior. This is the case of solution 1 and 4. However, if the series components are of different type, summing up their reactance and replacing with an equivalent component at resonance frequency will bring a new circuit whose bandwidth will be in general wider than that of the original circuit. Thus, for solution 2 and 3, it's not recommended to replace the LC circuit by an equivalent L component or C component at resonance frequency unless we tolerate a wider bandwidth. Finding the previous results using the Smith chart is quite easy. The resistor Rp equals 25 ohm is used to normalize other impedances. First, we locate Zg and Zl and Rpi. Obviously, the latter will be at the center of the Smith chart. We have lowercase Zg equals 10 minus 4j and lowercase Zl equals 2 minus 6j. Then we read the corresponding admittances from the chart. As the components that will be connected to Rpi will be in series reactances, it suffices to consider the R circle passing through the origin of the Smith chart. The reactances connected to RL and Rg are in shunt configuration, so we will draw the G circles passing through them. We then highlight the intersection points named Mg1 and Mg2 for the left subcircuit and ML1 and ML2 for the right subcircuit, and we note the corresponding reduced impedances and admittances. To design the left subcircuit first solution, we have to move from Zg to the center of the Smith chart. The first step consists of walking in the counterclockwise direction from Zg to Mg1 on the G equals 0.085 circle. Thus, we add an inductor whose susceptance is B1 equals Bg1 minus Bg equals minus 0.315, which correspond to a reactance X1 equals 3.18. Thus, uppercase X1 equals 79.5 ohm. Afterwards, we move in the counterclockwise direction from Mg1 to the center of the abacus on the unity circle. Thus, we add a capacitor whose reactance is X'2 equals 0 minus 3.28, which is equal to minus 3.28. Thus, uppercase X'2 equals minus 82 ohm. To design the left subcircuit second solution, we have to move from Zg to the center of the Smith chart. The first step consists of walking in the clockwise direction from Zg to Mg2 on the G equals 0.085 circle. Thus, we add a capacitor whose susceptance is B1 equals Bg2 minus Bg, which is equal to 0.245. which correspond to a reactance X1 equal minus 4.08. Thus, uppercase X1 equals minus 102 ohm. Afterwards, we move in the clockwise direction from Mg2 to the center of the abacus on the unity circle. Thus, we add an inductor whose reactance is X'2 equals 0 minus 3.28, which is equal to 3.28. Thus, uppercase X'2 equals 82 ohm. To design the right subcircuit solutions, we apply the same method. The results are summarized hereafter. B3 equals BL1 minus BL, which is equal to minus 0.37. Thus, X3 equals 2.70, and thus, uppercase X3 equals 67.5 ohm. X2 equals 0 minus 4.4, which is equal to minus 4.4. Thus, uppercase X2 equals minus 110 ohm. Then, B3 equals BL2 minus BL, which is equal to 0.07. So, X3 equals minus 14.3. Thus, uppercase X3 equals minus 357.1 ohm. And finally, X2 equals 0 minus 4.4, which is equal to 4.4. Thus, uppercase X2 equals 110 ohm. If the designed pi matching network doesn't bring a realizable circuit because of components value or because of its frequency response, an interesting alternative could be the T matching network. It comprises three reactances, x1, x2, and x3, in a star or Y configuration. Through Kennedy theorem, we can derive the T-matching network directly from the pi-matching network. However, the obtained T-circuit will not behave as the pi circuit does. Thus, we must develop the T-matching circuit from scratch, just the way we did with the pi-matching network. The design of the T-network comprises splitting the circuit into a left and right L-matching network. The middle reactance x2 is equal to the parallel combination of x'2 and x2. Instead of transforming ZL to the conjugate of Zg, we will transform Zg to an intermediate resistor RT thanks to the left circuit, and ZL to the same resistor RT thanks to the right circuit. In order for the design solution to exist, the resistor RT must be greater than Rg, and RT must also be greater than RL. Thus, RT must be greater than the maximum of Rg and RL. Here we apply twice the formulas developed for the L-matching network, and we get the expressions of the reactances x'2 and x1, as well as x2 and x3. Then we combine x'2 and x2 in a parallel combination to find x2. As we have two solutions for each subcircuit, we end up with four combinations, each having a specific Q factor. Choosing an intermediate resistor RT much greater than RL and Rg will definitely raise the Q factor of the whole circuit. Actually, we evaluate the latter by summing the Q factor of the left and right circuit. We get Qt equals Q left plus Q right. When the source and load impedances are real, the expression of the Q factor is simple. Here it is. Alternatively, we need to pay close attention to the evaluation of Q left and Q right. For instance, to find Q left, we must consider again positive terms in sigma x left and divide the result by 2Rg. Then, to find Q right, we must consider again positive terms in sigma x right and divide the result by 2RL. Consider at f equals 1 GHz, designing a T-matching network in order to match load impedance ZL equals 50 minus J150 ohm to a source impedance Zg equals 250 minus J100 ohm. The following table summarizes solutions obtained when applying the developed formulas when RT equals 500 ohm. Although the T-matching network is electrically equivalent to the pi-matching network, the results table and the following figures show different behaviors in terms of frequency response. In our example, the T-matching network provided wider bandwidth and obviously smaller Q factors. Thus, the T-matching network offers many more additional solutions to choose from. Let's find the previous matching solutions using the Smith chart. The resistor RT equals 500 ohm is used to normalize other impedances, as it is common to the two subcircuits. We locate Zg and Zl and RT. Obviously, the layer will be here again at the center of the Smith chart. We have lowercase zg equals 0.5 minus 0.2j, and lowercase zl equals 0.1 minus 0.3j, and then we get the corresponding admittances from the chart. As the components that will be connected to RT will be shunt susceptances, it suffices to consider the G circle passing through the origin of the Smith chart. The reactances connected to RL and RG are in series configuration, so we will draw the R circles passing through them. We then highlight the intersections points named MG1 and MG2 for the left subcircuit and ML1 and ML2 for the right subcircuit, and we note the corresponding reduced impedances and admittances. To design the left subcircuit's first solution, we have to move from Zg to the center of the Smith chart. The first step consists of walking in the counterclockwise direction from Zg to Mg1 on the R equals 0.5 circle. Thus, we add a capacitor whose reactance is x1 equal xg1 minus xg, which is equal to minus 0.3. Thus, uppercase x1 equals minus 150 ohm. Afterwards, we move in the counterclockwise direction from MG1 to the center of the abacus on the admittance unity circle. Thus, we add an inductor whose susceptance is B'2 equals 0 minus BG1, which is equal to minus 1, which corresponds to a reactance X'2 equals 1, and thus uppercase X'2 equals 500 ohm. To design the left subcircuit's second solution, we have to move from ZG to the center of the Smith chart. The first step consists of walking in the clockwise direction from ZG to MG2 on the R equals 0.5 circle. Thus, we add an inductor whose reactance is X1 equals Xg2 minus Xg, which is equal to 0.7. Thus, uppercase X1 equals 350 ohm. Afterwards, we move in the clockwise direction from MG2 to the center of the abacus on the admittance unity circle. Thus, we are adding a capacitor whose susceptance is B'2 equals 0 minus BG2, which is equal to 1. It corresponds to a reactance X'2 equals minus 1, and thus X'2 equals minus 500 ohm. To design the right subcircuit solutions, we apply the same method. The results are summarized hereafter. X3 equals XL1 minus XL, which is equal to 0. Thus, uppercase X3 equals 0. B second 2 equals 0 minus BL1, which is equal to minus 3. Thus, X second 2 equals 0.33, and thus, uppercase X'2 equals 166.7 ohm. Then X3 equals XL2 minus XL, which is equal to 0.6, which corresponds to uppercase X3 equals 300 ohm. And finally, P second 2 equals 0 minus PL2, which is equal to 3, leading to X second 2 equals minus 0.33, and thus X second 2 equals minus 166.7 ohm. The last circuit we will discuss in this video is the double L matching network. Our aim with this design is to achieve a reduced Q factor, which will result in a broader bandwidth. As the name implies, we will consider cascading two L matching networks to achieve this goal. So instead of converting directly the load impedance to the conjugate of the source impedance, we will take a further conversion step by considering an intermediate resistance RD, whose value is between RG and RL. In the following figure, the right subcircuit will convert ZL to RD, while the left one will convert RD to ZG. From the equations derived for the L matching circuits, we deduce that the subcircuits can exist if RG is greater than RD, which must be also greater than RL. Applying twice the formulas of the L matching network provides the expression of the reactances X1, X2, X3, and X4. Once again, 4 matching circuits are possible, and the choice will be based on the desired Q factor and bandwidth. A good approximation of the Q factor is the product of the Q factor of the two subcircuits. We write QDL equals Q left times Q right. When the source and the load impedances are real, the expression of the Q factor is simple. Here it is. Otherwise, we must focus on the evaluation of Q left and Q right. For instance, to find Q left, we must consider again positive terms in sigma x left, and then divide the result by 2RD. Then, to find Q right, we must consider again positive terms in sigma x right, and divide the result by 2RL. Consider at f equals 1 GHz, designing a double L matching network to match a load impedance ZL equals 50 minus J150 ohm to a source impedance ZG equals 250 minus J100 ohm. The following table summarizes the solutions obtained when applying the developed formulas while choosing the intermediate resistance as the geometrical average of the source and load resistances. RT equals the square root of RL times RG, which is equal to 110 ohm. All solutions exhibit selective behavior with an average bandwidth greater than that of the previous impedance matching solutions. To find these solutions thanks to the Smith chart, it suffices to apply twice the method that was shown for the L matching network. This ends this video, hoping you enjoyed it. See you soon!